In this video, we're going to talk about pendulums and simple harmonic motion. To begin, let's discuss the defining equation of simple harmonic motion, or SHM. The defining equation of simple harmonic motion is that the acceleration of an object, which I'm going to write this as a second derivative of position with respect to time, is equal to the negative angular frequency squared times position. However, for pendulums, the position is going to be angular, so we should write this in an angular form. Theta is angular position, and the equation will be some maximum angular position, theta max, times cosine, angular frequency times time. And then if I take the derivative once to get the velocity of something rotating, the angular frequency omega will come out, and cosine will become negative sine, and the theta max stays the same. Then if I take the derivative one more time, I'll get the second derivative of position with respect to time, which is the acceleration, is equal to negative omega squared because another omega is going to come out of the argument. Theta max, and then sine turns into cosine, and there's no sign change because the derivative of sine is just a positive cosine. Okay, now here we have something very interesting. It is that theta reappears in the acceleration equation. And so we can rightly say that the second derivative of position with respect to time for angular objects is the negative angular frequency squared times theta. So notice that these equations are very similar. And because these equations have a function, so x and theta, then the second derivative of that function, so this right here or this right here, we call these second order differential equations, or diffie EQs, as many people lovingly or hatingly call them. We'll use these in our pendulum problems. So let's take a look at something that's incredibly convoluted and unnecessarily difficult. The simple pendulum. Using Newton's second law in rotational form, write a second-order differential equation and solve for the period of the pendulum in terms of its length L and any other natural constants. A lot here. This really is not a difficult problem, but there's a lot of code happening here. Using Newton's second law. Newton's second law is that the net force equals mass times acceleration in rotational form. That means look at torque. The net torque is equal to not ma, but I alpha. Now, you could look at net forces to find the period of the pendulum, which is what we're looking for here, t. But torque ends up being a little bit easier for this problem. To find the torque, though, we still will have to draw forces. So let's draw some forces on the pendulum bob. This little mass thing right here is called the bob. Hi, Bob. So as the bob moves up, gravity will pull down. And tension will pull up along the string, which the string has a length of t, and that'll be important in a bit. If I draw the weight force, as components that are parallel and perpendicular to the string, then I can see that theta should go here, because theta is here. It's also here. And I'll get two components of the weight force. One is mg cosine theta, because theta is adjacent to that angle. And then the other one is mg sine theta. Now, if I look at these forces, T and mg cosine theta, those two forces are going to create centripetal forces that change the direction of the pendulum. But mg sine theta is perpendicular to the length of the string. And so there will be a torque produced by it. Now that torque will depend on mg sine theta and the radius. So that radius is L. And we can say that the net torque is mg sine theta times L. Now there's something a little bit strange in this problem, and that is that the angular position theta is always, or when it is, counterclockwise, then mg sine theta is in the opposite direction or clockwise. This means that we need to make mg sine theta negative. And it's what we call a restoring torque, much like we would say something like negative kx for a spring. Negative mg sine theta is a restoring torque in this problem. Okay. Next, I have the moment of inertia I, and for a small ball, the moment of inertia of a little particle or a ball and string is always mr squared. Except again, our radius isn't r, it's l, so I would write ml squared. So ml squared. And here I have an angular acceleration, which I can express as the second derivative of position with respect to time. And so that's what I'm going to do. But remember that the derivative, second derivative, with respect to time, is a differential equation. And here, I'm very close to having this second order differential equation thing. How do we get there? Well, we use something called the small angle approximation. The small angle approximation is simply that when sine theta is really small, it's actually equal to theta. Typically, we say for angles that are less than 15 degrees or 0.26 radians. Let's take a look at that. Okay, here I have my calculator, and if I check my mode, I'm in radian mode. This really only works in radian mode. And if I do sine of, let's say, 0.05, then what I'm going to get is 0.049. Well, that's basically 0.05. If I do sine of 0.1, I'm going to get 0.099, which is basically 0.1. And this will go on until I get to 15 degrees, which is 0.26, so 0.26 radians, 0.257. And then I'll start to get a situation where in radians, the angle theta, sine theta, is a little bit different. But for small angles, less than 15 degrees, or 0.26 radians, I can just say that sine theta really is equal to theta. And that's what we're going to do here. So what that means is my sine theta here, I can just rewrite as theta. Negative mg theta times L. And this second derivative here, I can replace with the acceleration. I'm sorry, the key, the defining equation for simple harmonic motion, which is negative omega squared times theta. Now, doing this, I can get rid of m, I can get rid of the negative, I can get rid of theta, which is crazy, and I can get rid of one of these l's. What I'm left with is g equals L times omega squared. And if I solve for the angular frequency, I'll get that omega is the square root of L. That's right. G over L. But we're asked to find period. So if we use the common equation, period is equal to 2 pi over the angular frequency, then I can plug in 2 pi over G over L, which I don't like that. That looks kind of gross. So instead, what I will do is say 2 pi times multiply by the reciprocal. Not G over L, but L over G. And this is the period equation. Often this is called the pendulum period, and so we'll put a little p next to it, just like that. All right, so that's the simple, not so simple pendulum equation. The next kind of problem is going to make use of something that we don't necessarily need to know the moment of inertia for. Like we used this moment of inertia here because we knew it was just a ball on a string. But what if it was just some random object with an oddly distributed mass? I'm so glad you asked. So let's take a look at what's called the physical pendulum. The physical pendulum is any object that's moving back and forth. It could be a hammer, or it could be some weird-looking blob, or it could be a circle. Who knows? If it's physical and it's swinging back and forth, it's a physical pendulum. So, using Newton's second law in rotational form, write a second-order differential equation and solve for the period of a physical pendulum in terms of its length, rotational inertia I, and any other natural constants. That just means G. Can't remember if I said that. Okay. So, Newton's second law in rotational form. There's going to be a net torque acting on this physical pendulum or hammer. And that will be equal to the moment of inertia I times the angular acceleration alpha. What is the net torque? Well, it just so happens to be the exact same thing as before. Except now I'm going to need to figure out, you would often be told, where the center of mass is on your physical object. For a hammer, it's going to be towards the head, so let's say that the center of mass is something right here. If you didn't know that this crash test dummy symbol means center of mass, it means center of mass. Okay, well, that is where there will be a weight force down, mg. And of course, there will be tension in the handle that goes up, call that T. And just like before, if I draw components of mg that are parallel to the tension and perpendicular to the tension, then I'll get an mg cosine theta here and an mg sine theta over here. Same thing, mg sine theta is the restoring torque. And so I would say negative mg sine theta, that's the force, times, now I need a radius, and here's where things are a little bit different. Often on a physical pendulum, the distance between the point of rotation, which is usually called P for pivot or point, the distance between the point of rotation and the center of mass is what we want. So that won't be the length of the object, but instead it's this quantity that we often call d. So mg sine theta times d is equal to I alpha. It tells me to leave the rotational inertia as I in this equation, which I'm going to do. And then I know that the angular acceleration is really the second derivative of angular position with respect to time. Awesome. Now this right here, that's exactly what this is, a second order differential equation. Once I get rid of sine theta. So small angle approximation again. Sine theta is equal to theta for small angles. And so this would give me negative mg theta times d. I keep I. And now I replace the acceleration or second derivative with negative angular frequency squared times theta. A lot of canceling happens. Theta goes away. And there are no more negatives. What I'm left with is mgd equals I omega squared. So when I divide both sides by I and take the square root, I'll get that the angular velocity is equal to angular frequency is equal to mgd over the moment of inertia I. And because the period is equal to 2 pi over the angular frequency, just like before, what this is going to give me is 2 pi, and I could divide by mgd over I, or I'm just going to multiply by the reciprocal, so invert them, I over mgd. Great. This is what's known as the period of a physical pendulum. It's often written T-phys, which is hilarious. 2 pi square root of I over, oh my god. Useful equation. Whenever you use this, you have to use the moment of inertia I and then the distance d between the point of rotation and the center of mass to get something useful. So let's do a quick example of that. Determine the period of oscillation for a cylinder swinging about an axis that is perpendicular to its edge. What does that mean? That is so weird. Well, that means imagine you have a cylinder or a disc, and that cylinder or disc is rotating. I'm going to try and draw the cylinder. Oh, that looks terrible. Is rotating. Usually like a wheel, you would put the axis at the center, and it would rotate. And in fact, for a disc, the moment of inertia at its center of mass is 1/2 m times the radius of it squared. And we will need that, so I'm going to write that equation there. But now it's saying, what if instead of rotating it there, you are rotating it somehow at the top, right here. And so you're allowing this to oscillate back and forth like a physical pendulum, just like if you had a normal hammer or small ball on a string, whatever. And we can use our physical pendulum equation. So the physical pendulum equation, what we just wrote, T pi over I mgd. There's no need for us to do a fancy derivation and draw the restoring torque. Instead, what we want to do is figure out what the moment of inertia I is going to be. Now, because this is not rotating at its center of mass, we have to use a special theorem called the parallel axis theorem to get a new I that goes in our equation. So the parallel axis theorem states that a moment of inertia, I, about a parallel axis, so notice that the center and this edge axis, they're parallel to each other. Sometimes we say I sub p, sometimes we put a little prime. I'm going to put a prime. Is equal to the moment of inertia at the center of mass plus the mass of the object times the distance that it is from the center of mass squared. So here again we have that distance from the point of rotation to the center of mass. Now in this case, the point of rotation at the edge and the center of this disk are a distance of r away. So really what we should do is write plus mr squared. And the moment of inertia at the center of mass is 1/2 the mass times radius squared. Oh, so 1/2 mr squared plus mr squared, that's going to give me 2.5 mr squared, or, oh, what is that? Wait, I said the wrong thing. That's 3. There we go. That's 1.5. So 3 over 2 mr squared. There we go. Math makes sense. Okay, so this is the moment of inertia that we plug into our equation here. So 2 pi times, and we change the moment of inertia to be 3/2 mr squared divided by mg times d. But here we know that the distance d from the center of mass to the point of rotation is actually the radius of the circle, like we used before. So we can write mgr. And when we do that, we get a lot of cancellations. The mass goes away, and this radius cancels off one of these radiuses here. And so what we're left with is that the period of this physical pendulum is equal to 2 pi times 3r over, I'll bring this 2 down, 2g. And that is how you use the equation. There is one more rotational pendulum that does come up every so often, and it's called the torsional pendulum. A torsional pendulum is something that's going to rotate basically back and forth, kind of like when you were a kid and you would spin yourself in a circle on a swing and then let that swing unspin, and you would go back and forth, back and forth. That's what's happening here. There's some sort of rotation going this way. Now, in these problems, they're a little bit different. You're going to be given something called a restoring torque in an equation form. So let's look at this. Using Newton's second law in rotational form, write a second-order differential equation and solve for the period of the torsional pendulum that experiences a restoring torque of tau equals negative k delta theta in terms of I and k. Quick thing, whenever you see deltas, I put this in here on purpose. Remember, if we just say that the initial angular position is 0, we can get rid of it. Instead of writing delta theta, I'll use theta, just like I have been before. So let's start. Newton's second law in rotational form. Net torque equals I alpha. Now, in this case, I actually don't need to think about the geometry of the problem for the torque because I'm told what the restoring torque is. So I put that in for my net torque, negative k theta. And the moment of inertia, we're going to leave alone because it wants us to have that as a term. And the angular acceleration is the second derivative of the first position, angular position with respect to time squared. So here again, a second order differential equation. I've got theta and its second derivative. So I know that I can replace this. I know that I can replace this acceleration with the negative angular frequency squared times theta. And when I do that, wow, look at these cancellations. Theta's gone, the positives are gone, and I get a wonderful little equation, k equals I times omega. And so the angular frequency is just omega squared. The angular frequency is just equal to the square root of k over I, which is a pretty super useful equation, especially when we plug it in to our period equation. And we're going to get 2 pi times, again, multiplied by the reciprocal. So square root not of k over I, but I over k. And this right here is the period equation for a torsional pendulum, which that is often not derived on certain tests, and occasionally you'll be asked to do this, but a lot of the times you just need to know what this equation is to be able to find the periods for these types of problems. Okay, so in this video, we learned 3 equations. The first is that the period for a simple pendulum is equal to 2 pi times the square root of the length of that pendulum divided by g, which is the acceleration due to gravity or gravitational field strength, depending on how nerdy you want to go with it. The other period that we learned was the period of a physical pendulum. And that is 2 pi times the square root of the moment of inertia I divided by mgd, where d is the distance between the point of rotation and the center of mass. And then our third period equation torsion, I don't really know what to call it. Let's say torsional. The period for a torsional pendulum, which is going to turn out to be 2 pi times the square root of I over whatever k is. K is always going to be some constant. It's very similar to when we use like mu k in the friction force. But anyway, these are our 3 periods that we've derived. Congratulations. You are awesome. Why did we decide to learn physics? Goodbye.